Cheers.
Great. Next, I'm delighted to introduce you Tom, who has nearly 20 years of experience helping customers achieve innovative projects through application of simulation. Can I first inquire if Tom is with us, because I was seeing it.
I am, Ajit. Can you hear me?
Yes, I can. Great. And on a personal front, besides doing excellent stuff at Altair, Tom enjoys watercolor painting, running, and is learning to play the piano. So, Tom, over to you.
Yeah, thank you. Thank you for that, Ajit. Let me just share my screen here in the first instance. Yes, thank you for the introduction, Ajit, and thank you indeed for inviting me along to present today. So, yeah, I've spent my career at Altair almost 20 years now, as an engineer, as a design engineer, helping customers achieve innovative solutions through the application of simulation technology, optimization technology. So I sort of come at this problem from the sort of design engineer end rather than the academic end. So I want to talk to you today about efficient design for additive manufacturing, what we at Altair have done, what we want to do in this area. So I thought I'd start with a situation that's sort of common to me, at least, and I imagine is common to any other sort of design engineers that may be on the call at the moment. It's sort of illustrated by this little comic strip I put together here. I think we all know that industry increasingly demands greater innovation within shorter timescales. There's an ongoing trend with that, certainly. And this in turn demands better tools for the design engineer. As indicated in the presentations we had earlier, there's this definite need, isn't there? And the tools that can help the designer address the concerns they have, so that they're always under pressure to innovate. You know, how can they innovate quickly and produce these right first time solutions that not only meet these challenging performance targets, but are also manufacturable as well, and thus achieving these sort of efficiency goals, which are so in demand at the moment. And at Altair, we believe that the solution to this efficiency challenge is to put simulation, what we call simulation-driven design, in the hands of the design engineer. So what do we mean by simulation-driven design? Well, in short, it's using simulation technology to inform the design process rather than its traditional role of simply validating the design. And I think that's a concept which we all understand. And having access to the information that simulation can provide up front is really key to enabling the design engineer to create efficient, optimal, and manufacturable designs that meet performance requirements. And crucially, this technology needs to be made available without demanding expert knowledge from the design engineer in all of the different disciplines that they are going to be involved with in terms of coming up with a design. This, of course, is not to say that expert knowledge is no longer required. It's not all being buried in the machine. That knowledge is always very important and very valuable, but technology like this can help the designer to achieve a design that at least has the best possible chance of standing up to more detailed scrutiny by domain experts later on in the design process. So instead of using their own knowledge and experience to come up with something, it's using this technology to give them a boost towards a solution which is less likely to have to change as it goes further down the design cycle. So Altair's solution to this challenge is our software product called Inspire. So it's a product that combines the ability to generate optimal designs in the sort of designer-friendly CAD environment, something which a a designer is more familiar with than perhaps a computer-aided engineering environment. And it introduces the ability for the user to analyze those designs, both for performance and manufacturability. And of course, one of the manufacturing disciplines we support is additive manufacturing. And I want to show how Inspire helps with the design for additive manufacturing challenge. So this is showing you what we can do, what we can do at the moment. And we've got some various videos here, which I'm hoping are going to work without issue. So here we go. So this is Inspire. So obviously, in order to design for additive manufacturing, you obviously need to come up with a baseline design first, don't you? Something which you can then evaluate for its suitability for AM. And we all know very well that topology optimization is the perfect partner for additive, and Inspire allows designers to easily define and the package space and their loads and targets and explore these optimal structural solutions. And once the designer is happy with that, we also have the ability to quickly convert those concept designs into some prototype CAD, which will then enable us to perform evaluations in terms of its manufacturability. So in this particular video, you've just seen the results of a topology optimization, this one-click process where you can generate this prototype CAD off the back of that topology optimization. And then we're just merging some of the CAD components together here to form our part, which we can then go on to evaluate in the next step. So with the prototype CAD generated, the suitability of that design for additive manufacturing can be evaluated, and that can be done using this Print 3D module that we have within Inspire. And what's really important here is that you're not changing tools, so you're not needing to export the geometry, perhaps losing some design information along the way. You're remaining in the same tool, but having exposed to you different capabilities as we go along. So we're not forcing the designer to move out of an environment that they are familiar with into one that they are not familiar with. So we have the traditional steps that you'd expect from this type of process. So we can quickly show you those steps in action. So we can obviously pick the part which we want to evaluate for printing. We can then access our materials database, and we can pick the material which we want to manufacture it from. And you would have seen in there's various parameters that we can set in terms of the material properties, which are relevant for the simulation later on. We can obviously define the printing environment that the part is going to be built in as well. And then we can move on to defining the orientation. And of course, we have the traditional way of just spinning around the model, and we can save off a particular orientation and have a look at the support area, the support volume, the printing time, the things which add cost to manufacturing a part, and obviously the things which we want to try and minimize. So we also have these orientation optimization tools which can help with picking a good orientation. And this involves a heat map that is the average of 3 different parameters. One is the build time. The other one is the number of supports, the supported area. And then there's a geometrically based measure of possible deformation in the part as well. So you can dial these 3 factors up and down to adjust the heat map, and areas in green would indicate where those factors have been minimized, and areas in red would indicate where those factors are at their worst. So in this particular case, I'm just focusing on minimizing, say, supports, and I'm clicking around on this heat map and seeing how the part moves as a result of making those changes. And then we can sort of settle in on one which we think is going to be good in terms of minimizing the support structures. And we can verify the improvement, if you like, by recomputing the supported area and the support volume, the printing time, and seeing an improvement in that. So moving on to the next step then, once we've done that, then have the sort of standard approaches which you see in many tools for creating the support structures. So it'll come up with a nominal support volume to start with, and then we can move on to defining details regarding those support structures. So we can pick different support geometries from those that are available. So in this case, I can perhaps pick my rod supports. You've then got the various geometrical parameters that you can assign, and you can go and modify those supports. And you can have different types of supports for different regions, again, with all the various parameters available to you to adjust those. So we can then see the resulting support structure that we have there. We would obviously want to try and verify the design through simulation to start with. But if we're keen to get going on printing something, then we have the ability to export as well into the standard formats to be read into the tools such as Renishaw's Quantum, for example, that would interface directly with the machine. What I'm showing you here is the build simulation interface for the user, and they can run two types of simulations. They can do a thermomechanical simulation, or just a thermal simulation on its own. So this is done by layer, and we have various parameters that you can set here in terms of the laser velocity, power, etc., in order to align the simulation with what you expect to take place in your machine. And we obviously have this fast to accurate slider on here. So the idea with this simulation is to provide an indication to the designer whether they're going in the right direction or not. Obviously, if you set it to fast, then it obviously reduces some of the computationally intensive aspects of the simulation, and therefore the result may not be as accurate, but it may give you enough information to be able to say, actually, that's probably not going to be okay. I need to go away and modify my design to try and improve that. So the next video I've got here is showing a different structure in this case, and this is showing the result of the build simulation. So the build simulation comprises the layer by layer building that we have here. We then have a cooling step. So I can see I'm just stepping through here. It's obviously the layer by layer that we have on here. We then have the cooling step, and then we have the support removal step and the resulting spring back that can take place. And of course, we enable the designer to investigate how the part is deforming, any plastic strains that may be taking place, the stress and strain state in the component, so they can get a feel for whether there's likely to be any failures during build. And we can see how the temperature is changing in the part as well, to see how effective those support structures are as acting as heat sinks to try and take some of the heating away. So we provide this ability to view these results to try and inform the designer as to the viability of their design. We can turn on the undeformed part here so we can see how that compares. We can obviously take individual measurements, individual layers, identify minimums and maximums, and we can generate as well graphical plots as well of all these results, so we can see how they vary over the simulation step. also. So, of course, the real power with this process comes from the ability to change the design and reevaluate it, because of course we're all in one environment. You can go through that process, do your simulation, gather this simulation-driven design information, draw some conclusions, and go away and look at modifying your design to maybe improve the outcome. So because we're all in one environment, we can, for example, as I'm showing in this case, we can come back to our package space, which was originally used to describe the package in which the part must reside. And it may be that we need to make some design changes. For example, in this case, the package space may have changed. So we can make some quick modification to that package space, and we can reevaluate the optimum solution and see how that changes following changes to the package space. It's not limited to rerunning your topology optimization. It may well be that you want to come back and just tweak some aspects of your CAD design without rerunning any kind of topology optimization. So you can, of course, do that as well. So it's playing on this idea of having a single environment that's familiar to the designer, that is enhanced by this simulation capability for coming up with optimum designs to start with and helping them understand whether it's going to be viable from a additive manufacturing perspective as well. So we can see a slightly different design in this case, and of course we can go ahead and convert that into a CAD interpretation at the click of a button as well. So that's what we can do at the moment. So it's providing that sort of basic level of support to the designer, so they're not going in completely blind to the prospect of having to design a part for additive manufacturing. They can undertake this simulation-driven design in order to inform them more about the viability of their design before that design then moves further down the design cycle. And as I said before, it's reducing the risk of that design having to change later on because the designers failed to account for something early on in the design process. So future plans, where do we want to go? What's coming up soon? What are we thinking about? Very soon, next year, we are going to be introducing support for the binder-sinter method to additive manufacturing. So we recognize that binder-sinter in some applications is a very attractive approach to doing additive manufacturing. And so we have a workflow suited to that as well, which is somewhat similar to what we've had for the laser powder bed fusion, where we can pick up parts, we can define the parameters of our oven where the sintering is going to take place, we can set our orientation, and we can define the setters, the ceramic setters that are needed to support the structure during the sintering process. But again, the real value comes from the simulation, and so we can run the thermomechanical simulation to predict the part shrinkage, how it's going to deform with or without the setters. And of course, we can run a compensation based simulation instead. So we can see how we might need to compensate the geometry to start with to achieve the desired shape at the end without perhaps the need for as many setters as you would ordinarily need in the binder-sinter process. Obviously, the need for setters can somewhat limit the geometry that you can produce using this technique. And if you can capitalize on this geometry compensation, then that can help you perhaps achieve a more complex design using this technique. So it's again exposing this technology to the designer in a way that they can understand the results and make informed design decisions from that. In general, though, what we want is more information for the designer faster. And this sort of plays into what's been discussed in other presentations today. We of course need faster simulation. Thermomechanical simulation, what we're doing at the moment, is good, but it can be slow, especially for large and complicated structures. We want to introduce inherent strain methods. Obviously, it's been pointed out already, they've been around for a very long time. They're well understood. People understand how they can introduce that method and get the material data necessary to produce meaningful results. So we want to expose that to the designer as well. We also want to capitalize on some of the learning we've taken from research projects that we've been involved in the past. So one of those projects is the Encompass project, which we were involved with about a year or so ago. And that really highlighted something which has been addressed already in another talk, is the need to account for post-build issues. It's not sufficient to simply say, I've designed my parts, I'm confident that we can build it. You also need to be confident that you can achieve your post-build processes as well. So, for example, are you going to need to do any surface finishing at the end? It will be useful to have some kind of surface finish prediction, maybe, to aid with that. And then you could couple that with some accessibility simulation to see whether you're actually able to get the finishing tools into the parts of the structure that you need to perform the operation. And also being able to identify how easy it is to remove the supports as well, whether you're introducing supports into inaccessible regions of the component. And also with inspection as well. I mean, if you're going to industrialize these parts, then they need to be inspectable, and you need to be able to do that reliably as well. So it's introducing tools to enable that inspection to take place. And the last point I have on there is cost-driven part orientation. At the end of the day, if you're going to be producing lots of a component, then cost becomes very important. And it becomes important to include within your orientation optimization some measure of nestability, how many parts you can fit on your build plates, what's the best orientation for that. Obviously, more parts per build, the lower the cost. Then you can start bringing in the trade-off between the build cost and the post-processing cost, and that trade-off between minimizing support structures and maximizing the number of parts you can put on the build. So we are always looking for ways of putting more information in front of the designer. But of course, our challenge is always how to put that information in front of the designer in a way that they are going to understand, which is really, really important and sometimes difficult to achieve. So that concludes my presentation. I may have been a few minutes over there. Thank you very much.
Thank you, Tom, for your talk.